Before we take a look at number 8, one thing I want to point out about problems like number 7. We'll see some more like this. Well, one thing you can look for, if we have an antiderivative that has cosine and sine in it, and one of those is raised to an exponent, generally, 99% of the time, if not 100% of the time, that is what we're going to set as u, whichever one of these is raised to an exponent. So we have cosine cubed, then the cosine of whatever it is in here is going to become our u. Now, that's not always the case with other ones. As we look at number 8, we can do that number 8 this way. There's actually two ways to do this one, which is rare. But we can kind of use the same idea. We have tangent of x and secant squared, right? So secant is being squared. So we can say u is equal to secant of x. Du, derivative of secant, is secant of x times tangent of x dx. So now think about this, right? Really what we have here is tangent of x times secant of x times secant of x dx. Right? Normally we would go ahead and say, okay, u squared times dx and the tangent of x. But seeing that our du is secant times tangent, we need one of those secants for our du. Right? Secant of x, one of these, we'll just say this one, is going to become u. But for our du, we need a dx, we need a tangent, and we need a secant. So everything's represented here. There aren't any numbers that we have to multiply inside and outside by. We just need to go ahead and rewrite this. So we have antiderivative of the secant part becomes u, and all of the blue part becomes du. So we just have the antiderivative of u times du. So if we do the antiderivative, we end up with 1/2 u squared plus c. So that's 1/2 times secant squared of x plus c. Like I said earlier, there's actually two ways to do this one, which is rare for integrals. But let's look at this original one. Actually, if we set u equal to tangent of x, du would be secant squared dx. So tangent of x, that becomes our u, and secant squared of x dx, that becomes our du. So we end up kind of with the same thing here as we did up here. Antiderivative seemingly is the same, 1/2 u squared plus c. But when we substitute back in for u, we end up with 1/2 tangent squared of x plus c. Right? These two things actually have the same derivative. They come out to be the same thing. If you look at it, derivative of this, we'd bring the 2 out in front, so it becomes 1 times secant of x, times derivative of secant is secant tangent. So secant times secant tangent would give us secant squared times tangent. Down here, bring the 2 out in front, we'd get 1 times tangent of x times derivative of tangent is secant squared, so we'd end up with tangent times secant squared. This doesn't happen with most functions, but it can with trig functions because they are periodic.